RL circuit. Consider the circuit shown in figure. Let epsilon be 36 volts, R0 50 ohms, R 150 ohms, and inductance 4 henries. Part A. Switch S1 is closed and switch S2 is left open. Just after S1 is closed, what are the current I0 through R0 and the potential differences VAC across R0 and VCB across R and the inductor L? Well, what is the value of the current through the inductor before S1 was closed? Obviously, this is an open circuit. It's going to be 0. So we know that in part A, the value of the current through the inductor at t is equal to 0 minus is equal to 0, and this must be equal to the current through the inductor at t is equal to 0 plus right after the switch is closed. Why? Because the voltage across the inductor is L di dt, and the current through the inductor cannot change instantaneously. If it does, it would imply an infinite voltage. Okay, so with that, I can say that the current through the resistor R0, I0 at t is equal to 0 plus, right after the switch is closed, is equal to the current through the inductor at t is equal to 0 plus, which is 0 amperes. So there is no current flowing through this branch at t is equal to 0 plus. What is the voltage VAC? Now remember, VAC is the voltage across R0. I have just told you that the current through R0 is 0. So using Ohm's law, I0 R0, this is equal to 0 volts. What is the voltage across the resistor R and inductor L? Well, looking at the Kirchhoff voltage law here, VAC plus VCB is equal to epsilon. So I can see that since there is no current flowing through this resistor R here, VCB is actually the voltage across the inductor L, and it is basically equal to the epsilon, the source voltage that we're providing, because there is no voltage drop across R0 or R. So we know that VCB is equal to RI0 plus VL, which must be equal to epsilon. And since I0 is equal to 0, there is no voltage drop across this resistor. And therefore, we know that VCB is epsilon, which is 36.0 volts at t is equal to 0 plus. Okay, so let's think about part B of the problem. After S1 has been closed a long time, S2 is still open, so that the current has reached its final steady value, which means we have constant current. What are I0, VAC, and VCB? Okay, now the voltage across the inductor V sub L is equal to L di dt. This time the current has reached its steady value, so that there is no time dependence of the current. L di dt is 0 at steady state. Now, then, if there is no voltage drop across the inductor, then the current I0 will be due to the series combination of these two resistors R0 and R connected to this power supply. So I will see that I0 is epsilon, the source voltage, divided by the total resistance R0 plus R, and that's equal to 36 volts divided by 50 ohms plus 150 ohms. So I will see that the steady state current I0 is 0.180 amps. And what is the voltage across the resistor R0? It is R0 times I0. So that's going to be 50 times 0.18. So I will see that VAC is 9 volts. And what is VCB? VCB is the voltage drop across R plus VL, which is 0. So this is going to be 150 times 0.18 plus 0. So that will give me a VCB value of 27 volts. So I know the limiting values of both voltages VAC and VCP and I0 right after the switch was closed and a long time after the switch was closed. Part C, find the expressions for I0, VAC and VCB as functions of time t since S1 was closed. Your results should agree with part A when t is equal to 0 and with part B when t goes to infinity. Graph I0, VAC and VCB versus time. Now, when this switch is left open, this switch is closed. Using Kirchhoff voltage law here, I have I times R0, I0 R0, I0 R plus L di dt, the voltage drop across the inductor, equal to epsilon. So that's the differential equation I have to solve to find the current as a function of time. So in part C, I write Kirchhoff voltage law, which is telling me I0 R0 plus I0R plus L di0 dt minus epsilon is equal to 0. So that's following this loop here. So you can see that I started at this point, point A. So I have I0 R0, I0 R, L di dt minus epsilon equals to 0. So that's the differential equation. So if I isolate L di0 dt, I will have L di0 dt is equal to epsilon minus I R0 plus R. So if I divide both sides by R0 plus R, then I will have L divided by R0 plus R di0 dt is equal to epsilon divided by R0 plus R minus I0. So this gives me, if I divide both sides by epsilon over R0 plus R minus I0 and multiply by dt, this will be the integral from the t equals to 0 value of the current I0, which is 0, to its value at time t, I0 at time t, di0 divided by epsilon over R0 plus R minus I0, that's equal to R0 plus R over L dt from time t equals 0 to t, R0 plus R over L dt. Okay, so I have to perform this integral. So what I'm going to do is let u is equal to epsilon over R0 plus R minus I0, so that du is equal to minus di0. With that, this integral will become integral u value at time t is equal to 0 to integral to the limit when it's time t. di0 is minus du divided by u. This is integral of minus du over u, which is going to give me natural logarithm of u0 over ut. Why? Because the minus sign will change the limit. So this will be from ut to u0. So that's natural logarithm u0 over ut. So if I substitute that here, for u, epsilon over r0 plus r minus I0, I will obtain natural logarithm of u at time t is equal to 0, where the current at t is equal to 0 was 0, so it is epsilon over r0 plus r. And then I have epsilon over r0 plus r minus I0 at time t. This is equal to the other side of the integral, r0 plus r over L dt. That just is going to give me t. So r0 plus r over L t. So if I take the exponential of both sides of this equation, I will find epsilon divided by r0 plus r is equal to epsilon over r0 plus r minus I0 at time t multiplied by the exponential of this term. So let me move this to the left. So this is exponential of r0 plus r divided by the inductance L t. So if I take this exponential to the left-hand side by multiplying both sides with e to the minus r0 plus r over Lt, I will obtain epsilon divided by r0 plus r exponential minus r0 plus r over Lt is equal to epsilon over r0 plus r minus I0 of t, which will allow me to isolate I0 as a function of t. I0 as a function of t is then given by epsilon over r0 plus r parentheses 1 minus exponential minus R0 plus R over L T. Okay, so you can see that here, if this goes to the left-hand side, this goes to the right-hand side with a minus sign, epsilon over R0 plus R parentheses, 1 minus the exponential, gives me I0 as a function of time. So that's my answer for I0 as a function of time. If I plug in the numbers, for I0 of t, I will get 36 volts divided by 150 plus 50 ohms, 1 minus e to the minus t, R0 plus R, 200 divided by 4 henries. So this will give me the final answer for I0 as a function of time to be 0.18, 1 minus e to the minus 50 t in amperes. Time in seconds, the current is in amperes. So that's my final answer. Okay, so that's the symbolic answer. Now, what about VAC as a function of time? VAC is the voltage across resistor R0. It's I0 times R0. So that's 50 times I0. So if I multiply I0 by 50, I find VAC as a function of time. And 9 times 1 minus e to the minus 50t in volts. All right. And since VAC plus VCB is equal to epsilon, that's from Kirchhoff voltage law, I know that VCB is epsilon minus VAC, so that will be 36 minus VAC. So then I can write VCB as a function of time as 36 minus 9, 1 minus e to the minus 50t. And finally, this can be written as 36 minus 9, 27, plus 9 e to the minus 50t in volts. That's VCB as a function of time. Now, I have these answers from part A. At t is equal to 0, I0 should be 0. T is equal to 0, 1 minus 1, it's 0. Part B says as t goes to infinity, I0 should be 0.18 amps. T goes to infinity, this goes to 0. That agrees with part B answer. Part A says at t is equal to 0, t is equal to 0, VAC is 0. That's correct. As t goes to infinity, it should be 9 volts. That's correct. And VCB at t is equal to 0, at t is equal to 0 is 36 volts. So 27 plus 9, 36 volts. T goes to infinity, this term disappears, we have 27 volts. So if I plot these, I0 starts from 0, goes to 0.18 amps in this manner. VAC starts from 0, goes to 9 volts, and VCB starts from 36 volts and exponentially decreases to 27 volts. So these are the graphs of time dependence of I0, VAC, and VCB, and they show the expected behavior when I check the limits in parts A and B. Okay, so in this problem we worried about another RL circuit. S2 was always left open, S1 was closed. Right after S1 is closed, the current, which was initially 0 through this branch, should be equal to 0 again, because the current across the inductor, through the inductor, cannot change instantaneously. So the current is 0, therefore the voltage drop VAC is 0, and VCB is simply equal to the source voltage epsilon. And as t goes to infinity after the switch was closed, we reach steady state. Constant current through the inductor L implies zero voltage drop across the inductor, which means the epsilon divided by R0 plus R is the current through this circuit, which is 0.18 amps. Then VAC is I0 R0, so that's 9 volts, and VCB is I0R plus the voltage across the inductor, which is 0, so that is also I0R, 27 volts. And in order to solve the time dependence of the current and the voltages, I have written Kirchhoff voltage law. After the switch was closed, I have I0R0, I0R, and L didt, the voltage across the inductor, equal to epsilon. So solving this equation by isolating I0 on one side and time on the other side and integrating from t is equal to 0 to t, I can obtain I0 as a function of time, as you can see here. And then VAC is simply I0R0 and VCB is epsilon minus VAC. So looking at the answers I get from this time dependence, I see a perfect agreement with parts A and B, and then I can plot the time dependence of I0, VAC, and VCB in this manner.